All right. We're ready to go. Mr. Hale here. This time Miss Scott is in the house.
I'm in the house.
So today we're talking about direct variation. Notice the equation that we have on the board. That should look familiar to all of us. What equation does that look like?
Are you asking me?
Yes.
It looks something like slope-intercept.
Which would be y equals mx
Plus b.
plus b.
Mm-hmm.
What happened to the b?
Well, I'm thinking if it's 0.
Very good. So in this case, this is a special case of slope-intercept form. This is a specific case wherever b equals 0. And what's a?
Well, since it's in the same position as the m, which is located next to x, I'm going to say it's slope.
Yes, it is the slope. It's specifically in this case, though, called the constant of variation, or the constant of, what's it, proportionality? Proportion?
I never heard that before, but okay.
Something like that, yeah. Right. But yes, it's called
Whatever you say, Mr. Hill.
So constant of variation, that's another word for slope. So we're going to specifically call it a, but it really is the same thing as n. It's the coefficient of x. X is going to still be our input, so y will be our output.
Oh, I get it, because slope measures steepness or a rate, and constant, it's varying at a constant rate.
Yes.
Oh.
You're very good, very good. So let's look at the next slide, and let's look at some examples of these. So the first thing we're going to do is take a look at which of the following represent a direct variation. So if we look at number 1, what form is that in?
Ooh, that looks like standard.
Yes, that is in standard form, and we want it to be in slope-intercept form. All right. So what I can do is, if I rewrite it, I want to isolate this y because I wanted to make it look like y equals mx plus b. First thing I can do is subtract 3x from both sides. So I get 5y equals 0 minus 3x.
Yeah.
So just be negative 3x.
Yes.
We don't have to write the 0. And our last step to isolate y, we're going to divide each side by 5. So we're left with y equals negative 3 over 5x. So in this case, do you think that represents a direct variation?
Well, it's in the same form as y equals ax.
Right? So and what does a equal in this case?
Since that negative 3 over 5 is next to the x, I think it's that.
Yes. So it's the slope, but more specifically, in this lesson, we want to think of it as the constant of variation. All right? So this is a direct variation because we don't have anything out here. Right? We're not adding anything. We have no y-intercept, or the y-intercept is equal to 0. All right, let's look at 2. 3 you can try by yourself. That is just like number 1. In number 2, we want to subtract x from both sides. So 2y equals 1 minus x.
Wouldn't that just be negative 1x?
Negative 1x?
Yeah.
They are not like terms.
Oh, okay.
So we cannot combine 1 and minus x.
Yes.
We can write it a different way. So we want to divide each side by 2. We want to divide each of these by 2. So this is 1/2 minus x over 2.
Yeah.
And let's say we want to put it in slope-intercept form. What is the coefficient here?
Negative 1x over 2, so that would just be negative 1/2.
So this is another way to write that. And then I'm going to write plus 1/2. So in this case, what's the y-intercept of this?
It's whatever is next to the ax part, which is positive 1/2.
So therefore, do you think that this is a direct variation?
That would be, no.
No. Why not? Why does this 1/2 make it not a constant variation?
Because it has to be 0, and that's not a 0, it's 1/2.
Okay. Yeah. So what we want to look at is you have an input, you're going to multiply that input by a constant of variation, and you're going to get an output. You can see in this problem, once your input is multiplied by the constant of variation, you're then adding something to it. So it completely messes up the whole direct variation concept.
Yeah.
All right, do we have any questions?
Nope, I'm good.
All right, you guys can try 3 on your own. The answer to 3 is that it is a direct variation. And we can talk about this more later, but just notice with the C value equals in standard form, and that the fact that it is a direct variation. I think that always works out that way, right? Yeah.
Well, yeah, and then the pattern too then is if you look at the A for the first one, it's negative 3 over 5. So using that same logic, then my constant variation other one is going to be positive 7 over 9. Right?
Equals A, yes. You are correct.
See, finding patterns and trends, Mr. Hale. You taught me that.
All right, let's just do a quick one here. What's the y-intercept of this first graph?
Looks like it's 4.5.
Yeah, let's say it's. Does it really matter? Even if it's 5, 4, 4.5, what does that tell us about whether it's a direct variation?
It's not.
It's not. So big old no. How about the second one? What's the y-intercept here?
0.
0. So that tells us that it is a direct variation. On this second one, by looking at the graph, how could we estimate what the constant of variation would be?
Wouldn't that be the slope?
Yes, it would be the slope. So from here, it looks like I go up 4 over 1.
Yeah.
You could probably go 3. It's really close in this area, but I would say 3 over 1, so that would just give us 3.
Okay. But you know, the important thing is...
Oh, no, 4. I said 4, but it could be 3. It's important to what?
What I was going to say is when you're using a graph, it's important to find, I mean, the point on the origin is obvious and easy to see, but to find the second point, you have to really make sure that that point lies on the corner of the box. Because then it's easier to
and
determine.
Both of these are close. So.
Yes.
We're just estimating here.
Yep.
All right.
Alrighty.
So let's take a look at the next slide. And here we have an actual problem that we can take a look at, see if we understand this. So we have this little chart. This talks about the number of tickets sold and the cost of those tickets. So first, is it a direct variation? So let's just look at this logically. If I buy 2 tickets and it costs $36, how much do you think one ticket costs? How am I going from 2 to 36?
Well, if 2 tickets are $36, one ticket is $18.
So it looks like I'm multiplying by 18. How about if I go from 3?
Move the arrow on the bottom. See that arrow on the bottom?
Yeah. All right. How about if we go from 3 to 54? What am I multiplying by?
18.
18. How about from 5 to 90?
18.
18. So if I'm multiplying by 18 every time, do you think that this is a direct variation?
Well, there's something constant about it. It's constantly being multiplied by 18.
Yes, so constantly being multiplied by 18 would suggest that A equals 18. So if A equals 18, what do you think an equation that we could use that represents this data?
So if y equals ax, which you said in the beginning, then if I replace the a with the 18, y equals 18x.
Very good. So that is our direct variation equation. So with this equation, we can now make predictions about the number of tickets that are not actually up here. So this is the whole point of what we're going to be doing, especially next class, is the ability to make predictions. So how much will 7 tickets cost? Simply 18 times 7, which is
126.
26. Whoops. Very good. Let's take a look at this second part. Suppose the ticket distributor charges $5.50 for each transaction, no matter how many tickets are purchased, and $18 per ticket. Is it reasonable to use a direct variation model for this situation?
No.
Why not?
Suppose the ticket distributor charges $5.50 for each transaction. Well,
let's just take a look at maybe the first one. How much would one ticket now cost?
$18 plus the $5.50.
Good, 18 plus 550, which is 23.50. Now 2 tickets. How would you go about figuring out how much 2 tickets cost?
18 times 2.
Good.
And then is it $5.50 again, or is it double that?
No, it's the ticket distributed. For buying a certain number of tickets is the transaction.
All right, so it's plus $5.50.
So this plus 550. So it's what? 36.41.50. So what if we were to make an equation out of this? If y was the cost, this number that's showing up here is going to be what?
The M.
X. See, here it was 1, here it was 2. So in general, it's x plus this 550 represents my y-intercept.
Mm-hmm.
So that does not look like a direct variation.
No.
All right, do we have any questions?
No, Mr. Huckner, you're such a good teacher.
All right. Here we're given some information, and we need to make a prediction about something else. So in order to make any predictions, we always need to know what A equals. So in this case, A is unknown. So if we start with the equation y equals ax, you can think back to when we were writing equations of lines and how we were trying to find B when it was unknown. So what's a way that we could find A?
Well, since A and X would be multiplied, I want to isolate the A to solve for it. So I want to undo the multiplying by dividing, and I want to divide by X.
So that tells me that y over x is always equal to A. This is a
So
really
every
good.
time, Mr. Hill, I just take the y and the x and divide them, and that gives me A.
Well, doesn't that look like it? I mean, what we did right here, since we used letters and we didn't substitute numbers, this works for any letters or any numbers that you want to substitute. So this works in general. So let's look at our example, 5, -2. That is x comma y. So A equals -2 over 5. So our equation is, so just like before, solving for A is not enough. You've got to write your equation. And now,
easy, Mr. Hill.
it should be very easy because we've done a lot of this stuff before as far as writing equations of lines. Now it asks us to make a prediction. And it wants us to predict what it's going to be when x is 20. So which should be -8.
It is.
So it's either -40 divided by 5 or -2 times 4. Do we have any questions?
No, I'm good.
Okay. Almost finished. Let's just
it's getting harder now.
graph these real quick. Does this look like a form that we would graph from?
No.
Not at all. What's messing it up? I mean, what's in our way?
4 next to the y is annoying.
Let's get rid of it.
Why are you dividing it? Why don't you just subtract it?
Well, this is 4 times y, so the opposite of multiplication is division.
Right.
Remember, we gotta remember inverse operations here.
Yeah.
12 over 4 is 3, so it's -3x. And we should
that
easily.
looks like direct variation.
It does look like a direct variation, and we can easily graph it. Where does this start? What's the y-intercept?
It's always 0, according to you, Mr. Hill.
I mean, according to me, yes, but does that make sense?
It does make sense.
Right, 'cause this is like
that's what
plus-
you told me, Mr. Hill.
This is like +0.
Yeah.
And then, how am I going to get... I didn't make it a clone. Oh well. How am I going to get the second point?
Just use the slope.
So-
Down 3 and over 1.
Over 1, there's no denominator here.
Over 0?
Is there really a 1 here?
Well, yeah, you know what? Now that I think about it, -3 over 1 is -3. It's the same thing.
So you want to put your point here.
Yeah, I don't think so. I don't like where that point is.
Oh, I made a mistake.
Did you do that on purpose?
I did not, actually.
I think you were as soon as I was paying attention.
I really did not. See, we all make mistakes. We always go right, and this is something I say all the time, and I didn't take my own advice. You should always count right because you want to make the negative the numerator. So we count down, or we fall by 3, and the run is 1. So does that look correct?
I think you need arrows in that middle one.
You are right. Man, picky audience today. Now does that look good?
Yeah,
Yes.
banging.
All right. Now we're doing the opposite. We're writing the equation y equals ax, and we're given a graph.
Oh, I can tell automatically it's a direct variation.
How?
It's going through the origin.
Good. So it's the key. And now I've got this point highlighted. So to go from the first point to the second point, I'm going up 1, 2, 3, 4, 5, and left 2.
So that's positive 5 because you went up, and left is negative. So it's like positive 5 over negative 2, which just becomes the whole fraction is just negative.
You are correct. So the way I would write it is y equals negative 5 over 2x. 5 halves x. That's it.
Boom.
All right, almost finished. Write the equation for the following direct variation.
I don't know. I think maybe they could do this at home. What do you think?
Well, let's just try 1.
All right.
This has no 0, so that doesn't tell us the y-intercept. Or, yes, it doesn't give us the y-intercept when x is 0. So what's another way I could look at it to try to find the constant of variation?
Well, I guess if you want to see if you constantly get the same variation.
So I'm going to look this way.
Yeah.
So what's 9 divided by 0.5?
18.
So I'm doing y divided by x here because earlier we learned that a is equal to y over x.
Mm-hmm.
What's 54 divided by 3?
18.
Negative 36 divided by negative 2.
18.
18 divided by 1.
18.
And negative 144 divided by negative 8. You need to get, do you think you need 18 for all of them or just most of them?
I think you need it for all of them. It has to be very constant the whole thing. Why is that not working? We're just having some technical difficulties here for a second, trying to get the.
We'll just hurry up.
Okay.
All right, so quickly, before
It's your
this
last
dies on us, y equals 18x.
Yeah.
All right, and that's it. Do we have any questions?
No, everything's perfect and easy.
All right, sounds good. We will see you in class, and we'll be doing some activities so you can understand this one.
Some conceptual activities
Yes.
that involve measuring.
That is true. All right, see you later.